Hello, okay, well, let's get started. For those of you who did not make the rotational solution stage, what we're going to do is we're going to go through the ESA mission. We're going to talk a little bit about the science. I'm joined here today by some lovely people from Teledyne who will also be talking through their contributions to ESA, and I'll talk through a little bit of the academics as well. We're hoping this is a little bit informal, so if you do have any questions, jump in. But please do just kind of raise your hands or whatever. And say whatever. I think our presentation will come out at 20 minutes, and then we'll mooch around, answer questions as well, and chat to everyone. To introduce myself, I'm Colin. I'm from the UK Space Agency. In the absence of an academic representative as well, I'm going to do my best to be one of the academics here today. But I think I'll defer a lot of the harder questions. To my right, I have Alan. Would you like to say hello?
Hello, my name is Alan Suter, and I am the ESA Project Director for Teledyne in Chelmsford.
Hello, I'm Christian Killow, and I'm from Teledyne Qioptiq, and I'm going to work on the imaging system.
Great, thank you so much. So I'll first go through, and I'll explain it of ESA and gravitational waves and how it detects them. To start with, what is ESA? ESA is an ESA mission. It's a large class mission, and it's a gravitational wave observatory. So gravitational waves are a new way of looking at the universe. Most of what we know about the universe is light. Light obviously has its limitations. I was going to put it to the class then as to what those limitations are, but we'll maybe try that later on in terms of audience participation, so be ready. But things that are dark, for example, black holes, we can sort of probe that. We can probe the extreme special relativity. We can probe the early universe. We can probe things that are far away as well. So let's go into what gravitational waves are. So to start off with, gravitational waves are ripples on space-time. So space-time is the fabric of the universe. It's normally shown in 2D, like this. It was one of the things theorized by Einstein. Gravitational waves came out of this special relativity, general relativity. You normally see it as a mat. You sometimes will have seen these experiments where they put things on a piece of latex or something, and it'll dip in, and that's an analogy for gravity. What happens is when there's something moving and it's asymmetrical, you get these ripples going out, and that's what a gravitational wave is. So it has to be asymmetrical. If you imagine, I used this analogy earlier, which is the swimming pool analogy. So if you imagine you're in a swimming pool, your eyes are closed, your ears are plugged, and you have no other senses apart from the feeling of the surface of the water on your skin. As something happens in the pool, the ripples will come to you. You can detect it. You can infer from that what might have happened in another part of the pool, whether someone's dive bombed in or whatever. Similarly, if you're in some water and there is just a perfectly smooth sphere just spinning around, it's not going to make any ripples. It has to be asymmetric mass that makes this happen. So the key thing is, if we can measure gravitational waves, we can see the universe in a different way. It's not right. Great. So I've got a little bit of maths for you actually. None of the maths is too much for us, apart from I see someone from our Office of Chief Engineers is here, so might be a struggle. We have a springiness, I guess, of the universe, and you can describe springiness or stiffness through Hooke's law. So the force is Hooke's constant there, k times the extension. So if you imagine you've got a spring and you're pulling it, and it's within that regime, the more you pull it, the further you pull it, the more force it takes. And how much force that takes is a function of the stiffness. So a rubber band, the constant, Hooke's constant there is 50. It's quite easy to stretch. Car suspension, more so. Everything has a stiffness, I guess. So a skyscraper, if you want to try and push it down, it'll spring back up. 200 million there. And for space-time, it's extremely stiff. It's 10 to the power 42, which is the key to universe life and everything. So that's space-time, extremely stiff. And what that means is that in terms of things that will affect space-time for gravitational waves, it needs to be extremely massive, or it needs to have a very high acceleration approaching the speed of light, right? Be relativistic. And that's why we're using it for very extreme gravitational events. So this is an animation which I think is mesmerizing. We were just kind of stood here staring at it earlier. Of gravitational wave. It's a controller, and then you kind of see it's propagating this way. And if you've got something here, then you can see how it would stretch, and compress there. And that stretching and compression is very real expansion contraction of space-time. It is stretching. It's not a variation in gravity, which is what people sometimes think in terms of variation there. It's space-time actually stretching and contracting. If you can measure that, like I say, you can measure gravitational waves. So this is how we do it on the ground. It has been done. The first detection within 2015. Sorry, because it's mental. It's a little bit off-putting. The first one was in 2015. It was a black hole merger, I think. Is that correct? And the detection was done at one of these institutions. It's Virgo and LIGO, which is gravitational wave. And they have two arm lengths. Those arms are 4 kilometers long. And what's happening within those arms is this interferometry. So a laser comes out, it's split up here with a mirror that splits up. One goes down one arm, one goes down the other arm. The light darts across, they hit the mirror, they get bounced back, they recombine. Yeah. And of course, light has a wavelength. So as it goes out. In phase gets split, it goes along, and then when it comes back, it combines. And depending on how it recombines, you'll get a signal coming out of the detector. So as these move, let me just go back a second. Should have messed with it. As these kind of wobble, the arm length changes, which means the phase will change, which means what you read will change. So you can kind of see these wobbling as a gravitational wave comes through. So as a gravitational wave comes through, the size of these arm lengths will change, and then you can read that, which is amazing, really. It's such an amazing sensitivity it can achieve. I mean, I've written down what it is. Over the 4 kilometers, it can measure something that's 1/10,000th of a proton. Which is incredible. And you can imagine like these mirrors might move because of something like the seismic, for example. It has to be isolated from all of that, and it can measure to that level. I mean, someone thought it wasn't good enough. There's problems with this on Earth. Does anyone want to suggest some problems with having something this sensitive on Earth? Oh, sorry? Cars, very good. Anything else that could change its moving mass on Earth? I guess it could be anything, right? So one of the things that was, I think, mentioned by one of you was waves crashing against the beach, clouds moving, stuff like that can interfere with this. But because they're all moving at a certain speed, what it means is you have to filter for certain gravitational events. And what those are high-frequency events, because they're not happening on Earth, so you can filter for those. So if you want the low-frequency gravitational events, you have to go to space. So someone thought 1/10,000th of a proton isn't quite good enough. Let's head to space there. This was meant to be sort of like a little bit informal, so if anyone does have any questions, I know some people have shown up, please do ask, and we can chat about it as we go. So in space it works very similarly. So this is a kind of mock-up of what LISA will look like. So it's got 3 spacecraft. Imagine these all in space. They're exchanging laser light in the same way as the last one was along the arms. What they're measuring is the distance between these things, these golden cubes, I guess, which are the taskmasters. And that's what this is. These are in free fall, and the distance between them all is being measured with these laser links. The distance between the spacecraft is 2.5 million kilometers, so a significant improvement on the 4 kilometers, and we'll talk about what that helps with in a second. So, thank you to UKDC for these slides. They are very fun. This is one of the benefits of going to space. The first one is space is quiet, so you get rid of these cars. You get rid of the waves, the clouds I've just been talking about. This cheeky little guy is an alligator, which I think is one of the things that they have at LIGO. But if this is a mirror, I'm not sure about how the maths kind of worked out, but I do trust the maths of Ewan who set this in. So if you imagine the mirror at the end of the arm, this is that mirror. The first gravitational wave signal, which is this, which was a 36 mass, sorry about that, a 36 mass black hole and a 26 mass black hole merging. They changed the mirror size by 10 to the minus 8 meters, which is insane. Over here, a nearby alligator, just by its force, not even by its moving, not by a gravitational wave, just by its gravitational force, and changed the mirror by 10 to the minus 7. So you have to account for that. So you can then search for lower frequency sources if you're in space, for the same reason as I mentioned before. And also, space is free in space. Like, it doesn't, once you're up there, I mean, space isn't free, as we all know, but once you're up there, once you're in space, making the arm lengths bigger is fairly easy if you're in a stable orbit. Which is what I mean by space is free. Here you have this measurement, which is the change in the arm length which you can achieve over the overall arm length. And this is LIGO, so it's a matter of kilometers size, and the arm length you can measure is this. And ESA, similarly, comes out around the same. The arm length is much, much bigger. Great, so I kind of put this in a show. We choose to go to space and do the other things, not because it's easy, but because it's quiet and free, which is JFK if you were to be alive right now. See, this is the orbit, which is, I think, beautiful. I think it's really nice. So it's not a Lagrangian, it's not orbiting the Earth, it's not orbiting the Moon, it's orbiting the Sun, it's in a heliocentric orbit. And it's just inclined, and each of these are on a separate orbit. And because of how the clever orbits work, they stay at equal distance to each other when they're in freefall, and they just keep going around. I think it's really beautiful. I think it's very clever as well. Yeah. So to give you an idea of scale and the things it can measure here, so this is the Earth-Moon distance. The distance between these spacecraft in this last one is similar to the Earth-Moon, 6 times the Earth-Moon distance. Earth and Moon, obviously not to scale there, but it'd be pretty in the sky if the Moon was that close and that big. Over that distance is measuring 1/10 the diameter of an atom, which is incredible sensitivity. I'm probably using the wrong word for sensitivity. If anyone knows the word I should be using, do correct me. But that's insane. And to put that in perspective, Earth to Alpha Centauri, 4 light years, it's about the same as a thickness of an A4 piece of paper. Which is incredible. That's the technology you can do here. It can be done. As far as we're aware, we sent the ESA Pathfinder up in 2015. Lots of the UK helped make that happen, including Qioptiq, who are here today. They managed to look at the noise, see it was feasible, and managed to see that it was 100 times better at what we needed it to do than what it needed. So it's 100 times better than we needed it to be. A real success story led to this mission, and it kind of shows how UK funding can help contribute and grow, and then move on to something else as well. So these are the things that we fund in the UK. So we fund the optical bench hardware. What the optical bench does is this kind of yellow thing. So these are the test masses that are in freefall, which are what we're measuring between. The optical bench measures the distance to the test mass from the optical bench, and it also measures the distance to the optical bench of the other spacecraft. And then that optical bench measures the test mass, and from that you get a distance between the test masses there. And they're both exchanging lasers over this amount over that distance. Which again I think is extremely impressive, but it's a really critical piece of the hardware, which is being done at UK ATC, University of Glasgow. And there's also lots of work being done on the data and the processing for ground segment at various UK institutions, and then also there is, of course, industry that are also contributing. I think as well, I think mentioned here is that we also that isn't our only contribution to this area, right? So black holes, for example, have X-ray missions, and it's the kind of thing where if we detect something, we can then link to other missions that we're also contributing to. For example, New Athena is an X-ray observatory, and you can work that in as well. And there's a UK contribution to New Athena. That's not to say, I mean, I've kind of declined the success story, that's not to say it's easy. It's extremely difficult, and I hope that's coming across in what I've shared so far. So this is an animation of the bench. So it's a square here, but it's actually on this kind of disc, and we use both sides. It's a little bit of a slow animation, but hopefully you can see the kind of contributions of various parts. So in green, what we do, the imaging systems, we'll be talking about later with Teledyne. The green is what the UK does. And then we can also see a constellation acquisition system here. So this thing here. which we'll also be talking about a little bit later on. But a really complicated piece of tech, and needs to be that should be good. That's a picture of the optical bench that was on Pathfinder. Yep. I was imagining it bigger, to be honest. It was 20 centimeters. Oh, and there's, sorry, just to finish off my little bit. A large part of what the work in the UK is doing is managing to bond these optics and do it automatically. So I think this is probably from the Pathfinder mission. This one, where's this from? This from Lisa. Nice. So it's bonding it, making sure it's stable, testing, etc., and also bonding various elements that are all very different from around the various contributions, and making sure that's all space ready. Great. So that's the UK contribution, and hopefully I've explained a little bit of the mission and the science. If anyone has any questions, we'll chat about it in a bit. But I'll pass for now over to thank you, John.
Thank you, Connor. Good afternoon, everyone. So my name is Alan Souter. I'm the project director in Teledyne for the ESA project. As Connor explained, our contribution is the constellation acquisition system. The constellation acquisition system is essentially the smart sat nav for the satellite to actually triangulate the three satellites together. It consists of 2 lasers going between each of the satellites. So in total, there's 6 lasers as you go around the 3 satellite systems. And that's the reason why we've got 2 optical heads on the bench that you saw. So each of those 2 optical benches, one is the laser going out to the other spacecraft, the other is the laser coming back in from the spacecraft. So what our system has to do is triangulate both those outputs and those inputs to actually get everything finally aligned. So the first stage is that we align through star trackers so that we've got a reasonable idea of where we are, and then we're looking to finely tune that with the lasers to actually get exactly where we are. Someone told me that in the mission profile, it'll take approximately 18 months for the lasers to finally actually attune themselves for the first one to acquire, then the second one acquire, the third, the fourth, the fifth, the sixth. Once that's all done, it will take quite a little bit of time to actually get it quite accurate. Once that's done, as Connor says, everything should be in a nice steady state, in theory, because space is free and nothing happens. In practice, little micro meteors, etc., can throw things a little bit off. So as well as our system being there to actually attune the system together at the start of the mission, we've also got to have the ability to switch back on having been off within 1 second so that we can then reacquire and do any final micro adjustments. Hopefully we're not doing that every second, otherwise we'll never get to a steady state. But that's essentially the science and the design that we have to accommodate. So, as I say, Teledyne here in the UK are the system prime. We work directly for ESA for this programme. We are then sending it on to the optical bench team who will then do the integration. So very much a close collaboration with, despite the fact it's ESA supplied, it's really ourselves that are really doing the prime work. We're joined by an optics company in Switzerland, Teledyne Alenia Space, who are doing the fine optics that they have done on various other elements. So we're coordinating not just the design for ourselves, but also the design with Alenia Space. As well as the optics side, we also are controlling the electronic side. So once we actually acquire those systems, it will go to our control electronics that will do some fine tuning on the processing of that image. So we'll take the raw image, we'll take various cuts of that image, and then build it down so it's a nice clear image that then the onboard computer can then do its stuff. Again, to give you an example, once all this laser light comes into the detector and goes into the onboard computer, actually the stray light around the laser will swamp the entire signal so much that we actually aren't able to measure anything. But then there's clever maths and algorithms that then will work out exactly where everything is. So it's a very complex stage process, which we feel part of. The last thing I want to say is, as well as Teledyne here in the UK and working with our colleagues in Switzerland, there's an extensive UK supply chain that we leverage as part of the geopolitical piece to actually contribute to the overall ESA programme. Does anyone have any particular questions on the constellation acquisition system at this stage? Okay, I'll happily pass over to Christian.
Thank you, Alan. So I hope it's been made clear now that the ESA will deliver fantastic science that we've been waiting for decades, and we've been waiting because it's so worthwhile having. But of course, to get that fantastic science, we have to build a fantastic observatory, and it's an incredibly complex observatory. And everywhere you look on it, the devil is in the detail. So it's fantastic that the UK is providing such a major contribution to this mission. We'll talk about one small aspect of the mission that would be obvious when you're thinking about it. You've seen the video that showed the optical bench, kind of a cartoon model of the optical bench. It is a very complicated optical system, but there are many places within it that things can go wrong. ESA Pathfinder demonstrated that we can do this kind of interferometry, and that we can get down to the sensitivity levels that we need for ESA. But there are additional things in ESA that weren't in ESA Pathfinder. One thing that we do know is that there will be a small amount of jitter in the laser beams. So the laser beams, as they arrive at the detectors, are moving in angle very slightly. And it's very, very slightly. But if you were to leave them to do their own thing, to do this, what will happen is this slight angular movement will appear on the detector as a longitudinal movement, as if you've moved your laser beam backwards and forwards. And that is what a gravitational wave will do to the signal. So our gravitational waves move the laser longitudinally, move it backwards and forwards. And if we have this tilt-to-length coupling mechanism in there, that will look like a gravitational wave. And when you do the maths, you find out that the amount of movement that we expect there to be in the lasers would wash out the gravitational wave signal completely, so we wouldn't see any gravitational waves. So that is a problem that needs a solution. Luckily, we have a solution. So the solution, one solution for this is to have imaging systems, pupil-to-pupil imaging systems. So if you have a pivot point here, so this is where your light is pivoting about, the jitter in real life, you wouldn't see it. It's tiny. It's a tiny amount of laser movement. But if you imagine it a bit exaggerated, your light has now changed angle. If these optics weren't here, it would come out to here. If this is your detector, you can see as you go up and down the detector, your path length has changed, and it makes it look like your longitudinal signal has changed. If you're clever with your optical design, you've got refractive indices to play with, you can have asymmetric surfaces, you can do all kinds of tricks, and you can manipulate your light so that it bends through these optics, and it doesn't matter what this angle is here, it still looks at your detector plane as if it hasn't moved. So this is the solution to the tilt-to-length coupling problem we have. So the people at Astronomy Technology Centre in Edinburgh have come up with an optical design as so. So the light comes in through a lens, through another lens. Space, as in footprint, is always at a premium when you're building spacecraft. So the beam is folded to make it compact, another couple of lensing surfaces, and then the light goes out to the detector. So this is kind of the implementation of this cartoon. It's a little 3D model of what it will look like there. So this is the design that Teledyne Qioptiq were given. We worked with ATC to make it manufacturable. We made some tweaks, some backwards and forwards, and this is the design we ended up with. This is a design that we wanted to demonstrate could be made in industry. It's the technology they use to join these pieces of glass for ESA Pathfinder and we'll use for ESA. You saw the little video of the component being put down. It's called hydroxide catalysis bonding. It's a glueless technology, so it's very good for space. There's no total mass loss, there's no outgassing or anything like that. It's incredibly strong, it's incredibly permanent. So it's a good way to build your optics for ESA, and we want to build the imaging systems in the same kind of way. But it is quite a tricky process to implement. We wanted to demonstrate that we could implement it in an industrial setting in our factory in St. So that was the first thing we had to do to actually take this process in-house. And once you've done that, then you have to align the optical system to meet the optical design. So that, as it turns out, that's positioning things at about 30 micron level of accuracy in about arc minute. So that's not a huge level of accuracy. It's the kind of thing that you can do with dead reckoning, with tooling, without having live feedback of the optical component positions. So we design tooling, precision tooling, get precision tooling made, make it, measure it, iterate, remeasure, make sure everything's in the right place. There are various tricks that can be played where you kind of build up your tolerances all from one way. There's lots of, again, the devil's always in the detail. There's lots of bits and pieces you can do to try and improve your end optical system by being clever with how you do your tooling. So we built some tooling. Here you can see the lenses bonded to their posts, a few silica lenses, a few silica posts, all bonded to a very stable 0-dio base plate. And probably about 2 months ago, Qioptiq delivered the prototype imaging system to the UK ATC, and it's now being measured. We delivered it with measurements, but it's now being interferometrically tested at the University of Glasgow. So it's great. It was a very successful prototyping program. We demonstrated we can do these kind of things in an industrial setting, and now we wait for the interferometric test results to come out and the engineering model and flight models.
Yeah, thank you. So I think that's almost, that is the end of the presentation. I'd love to get people's questions as well. We can hopefully answer any questions that you might have. If not, we will be milling around, so you can just come chat to us as well. But does anyone have any questions? Looks around, all around.
Tell them they can see the imaging system on our stand.
Oh, you can see the imaging system on their stand as well. A little reminder from Christian there. That imaging system that just went through will be on the Teledyne stand as well. Right, well, thank you then. What we'll do is we'll hang around. Please do come talk to us. You don't have to have a question necessarily, you can just introduce yourself. But it's been a pleasure, and thank you very much.